So let me just begin by thanking the organizers for what's a really wonderful workshop. Not only you invited me, there were really a lot of great talks. And honestly, I feel like there's I really enjoyed it, and I really feel like there's a tiny bit more of a community, at least in my perspective, now than there was 1 week ago. And I think that's a really amazing achievement. And the reason I'm saying this is because I'm feeling a bit bad, because the first part of my talk will be a bit about dissing the cavities and trying to kind of show the limitations of the field and what polaritonic cavities are good and what polaritonic cavities are not good. And I mean, I think I couldn't ask for a better introductory talk to the topic than what Angel just gave. And throughout the conference, we heard a lot about the analog between Floquet and vacuum engineering. And I mean, it's really an amazing and powerful technique, but there is kind of a catch to do with how good the cavity is and how much we need to confine. Because when you look down these numbers, you look at the formulas we had at the slides before, the amplitude of the vacuum field and the amplitude of the Floquet driving should be comparable. So that means that you need to have a big laser, sorry, a small cavity, which has the same vacuum field amplitude as a tabletop laser. And if nothing else, that's really weird. Okay, just think about it for a second, that you have an empty cavity and it has the same, megavolt per meter, or same order of magnitude at least, as the dark cavity and the big laser are the same thing. It's a really fascinating concept. And not only that, it really also kind of drives home the message of how interesting this is. Because if in the beginning of the conference, Jerome talked about tiny cavities which had fields of 5 volts per meter, maybe with screening it went up a bit higher, but this was the order of magnitude. Now we're talking about cavities which have maybe a megavolt per meter field. And I think the question is like, sure, we're expecting to see quantum Floquet, but I think we can honestly say that as theory-driven as the field is, it's also curiosity-driven to the point where I'm really curious what's going to happen here. And I totally believe what Angel just told us. I totally believe what the earlier discussions we had. But I'm really hoping they are at least partially wrong, and there's a big bunch of surprises on what's happening here that we haven't predicted yet. So this is kind of not theory-driven, experiment-driven, it's more curiosity-driven approach. And okay, and having said that, now that's the part where I want to actually ask, what type of cavities do we have, and what are the limitations? What do we need out of these cavities so they work? So the general, the macro cavity or the regular cavity, okay, that's the type we all know from school. That's the easiest one to describe and understand, also theoretically. And those have been presented by Fausti and others. Like, I don't think there is a lot to say there. They give you high quality factors, and but you don't confine light to an extensive degree. Now, on the other hand, you can go to the terahertz, as several speakers throughout this conference did, and that, you pay some price in the quality factor. It's no longer as high as it was otherwise, but you do confine light to an excessive degree. So we're talking about lambda over 1,000 confinement. On the other hand, you have lower photon energies. So now this is not a good thing or a bad thing, it's just a thing, in the sense that sometimes your energy scales match up to the terahertz scale, and you're happy. Sometimes, if you're talking about graphene, for example, the level of disorder is, just intrinsic charge disorder in graphene near charge neutrality point is on the order of 10 millielectron volt. So terahertz is problematic. So there's a lot to be done here, and I think we've heard a lot of these efforts already. I'll just mention there is another type of cavity you can think of, and I'm not going to really discuss this, but it's the extended Fabry-Perot-like cavity where you're confining light or basically in one dimension, or maybe even two if it's like a strip, but you're not controlling K completely. So you have multiple Ks and multiple omegas, and I think this was mentioned in previous talks. It's a slightly different creature. So when I'm talking about cavities, I'm talking now about 3D cavities. And when it gets to 3D cavities, excluding the terahertz regime, you can plot basically the type of cavities you have over here. And the good news is that we can confine light, infrared, also visible, extremely well. And each one of these blobs represents a different technique or a different way to generate cavities. And it was painstakingly taken by kind of actually looking through hundreds of papers and extracting the quality factors, which are always very clearly and transparently written. You know, it's of course very easy to find out what actually happens in every paper, but you know, so these are real numbers, and what you can see is that the achievements are just incredible. So the Pico cavities, also called gap plasmon cavities, or are like the extreme end. This is what happens when you have light, can be visible light actually, and you're really forcing it into a very small gap by just surrounding it by metal from all sides as much as possible. For example, particle and metal gap. So here, light, you're literally squeezing it into a very small volume, so it has a very high K, whether it likes it or not. The problem is you're paying with absorption, but we'll get to that in a second. But just to give you the comparison, the scale of the confinement here is on the order of 1 nanometer cubed. Okay, so if we're going to the previous slide, this is a field of quite a few gigavolts per meter, which is the limit where materials start to break down. So you have a cavity. If you could have a cavity which was 1 nanometer cubed, I mean, that's really a crazy regime to think about. And people have also been able to do, not reach exactly the same degree of confinement, but comparable degree of confinement with graphene and other 2D materials. And in theory, the quality factors here should be actually quite a bit larger. In practice, experimentally, this is the best that's been achieved, I think, is by Baslov's work on the order of 2030, something like that. So there are limitations there. And there's, of course, these less confined phonon polaritons, which I'll get to in a few slides. But I first want to just mention, what's the problem with these? Because, okay, it looks like the problem is solved. We have these really tiny cavities. What is the limitation? And it's really all about the quality factor. Because on the one hand, you know, if you think about Purcell factor, having a quality factor of 10 instead of 100 is not a big deal. It's just the Purcell factor is a bit lower, but it's still absurdly large in these cases. So who cares whether your cavity is a bit smaller? And it really comes down to what the quality is limited by. If it's limited by radiation, so you have basically your cavity and light is just leaking out, then it's actually not a big limitation. Instead of treating it, the cavity modes, there are proper modes which are evanescently decaying, there will be quasi-normal modes, but it's practically the same thing except they have a larger volume. And, you know, so again, your coupling is a slight bit smaller, but it doesn't change anything dramatically. The problem starts when you have absorption, because if you have a lot of absorption, so the quality factor is small, is like 5, like in many of these cases, because you have absorption. One way to think about it, there's a few different approaches to think about it, is that you're coupling light to a reservoir of two-level systems, and it generates phase noise. So you can you can treat it analytically in different forms, but it all comes down to phase noise, and that's a big problem because if you're looking at these cavities, trying to get all of these vacuum fluctuations is like trying to do the calculations Achim just mentioned while you're in a boxing ring and getting punched in the face once every cycle, you have the photon kind of being dephased or having a phase noise event, okay? Or actually more like twice every cycle. So it's very hard to, for me at least, to believe Angel's story if he's talking about these type of cavities, okay, with very, very low quality factors. Now, just to clarify, this is not to say that these cavities are not interesting or not useful. These cavities, I mean, to go to Juno's talk in the first day, these cavities are in the ultra strong, not strong coupling regime. Okay, that's kind of like later down the line from deep strong, because they are, you have a lot of absorption, just a second, but they are still very useful. Again, for example, there is a practical application of of extracting single photons from this type of cavity, which works remarkably well.
Thanks. I don't quite understand what Q radiative and Q absorb is. I mean, at the end of the day, I just measure Q. So, so how do I separate out these quantities? Or is this something that was manufactured for convenience, or by, not you, but I know it was introduced by others. But. So
the bottom line is you compare to simulation. It's not something you can measure necessarily, okay? I mean, so it's more like you have to compare, you measure Q, you just measure the bandwidth, and then you're trying to realize where it's coming from. It can come from radiation, it can come from absorption. Yeah, it's a good question, but there is no good answer.
I think just to mitigate a bit, on one hand, it's clear that as you make your cavity smaller, in a way you could say nature works for you, because there's the small antenna theorem that tells you that the Q, the radiative Q, actually improves, like the cube. Now, obviously, I would say your discussion really, in a sense, has it as a background to me, experiments where you're trying to extract light, you're not looking for a modification of the ground state. Because for me, it's unclear what the Q, even the non-radiative Q, does if you're trying to modify the ground state of a system by coupling it to a strong cavity. So that's maybe you're going to discuss it later. But you see, if the question is to of course look at some enhancement of the luminescence, yes, clearly, I completely see why having this very poor non-radiative Q destroys you, and actually you're sort of extracting very efficiently, you're emitting extremely efficiently, but you don't collect anything because everything is trapped inside these excitations. But it's, let's say, not so clear for me that this would be a limitation when you're trying to modify, for example, the ground state of a system.
So I'm not trying to say, what I'm trying to say here is really that when you're looking at a system that has a lot of absorption, the system you're looking in is intrinsically coupling additional, matter degrees of freedom, which you have to account for explicitly, and that typically, I mean, just solving the problem without these extra degrees of freedom is so complicated that nobody's even trying. I'm not saying I know what would happen if you add those matter degrees of freedom.
Wouldn't you think at the zeroth order you have a bosonic bath, and regardless of this are electrons moving around or photons, would that change something so much? So, you see what I'm trying to say? I mean, if you're in the perspective of looking at your system, which you have coupled to your cavity, whether, let's say, you're coupling to, a photon bath, which would be the ideal situation where you have an infinite Q, or if you're coupling to bosonic excitations, which are basically your electrons moving around, would that change so much? That's a bit my question. Why you say that it sort of changes? I mean, I'm really talking about the ground state. As soon as you're talking about excitations, I completely agree with you. This is obvious. You get this phase, you get this dephasing, and everything changes. That I totally agree. It's really, for me, the point of, let's say, if you're looking at the ground state.
So it really does come down to this problem that, again, the way I understand it, and from talking to your theoreticians, is that you're really your phase is becoming no longer defined. So your frequency or the energies at which your ground state is sitting, it's already it's a different entity that you're analyzing than the regular ground state. I'm not saying it's not going to do anything interesting. I'm just saying it's not going to do the same things which were calculated for the empty cavity without the disorder or absorption. Okay, so having said that, so this was the good, the bad, and of course there's also the ugly part, which is just differences between how these nonpolaritonic cavities behave. And for example, we heard a lot from Giano about exactly this longitudinal polarization, because we're in the quasi-static limit and light couples to matter a slight bit differently than it does otherwise. And similarly, to the dismay of theorists out there, you suddenly don't have any circular polarization. So you cannot break time reversal symmetry explicitly and make things topological. So it's just it's a limitation that you have to be aware of when you're going to these very small cavities. Not everything is the same thing, just shrunk down or just increased by a factor of 1 over square root of v. The good news, which I'm trying to hype up here, is that we came up with a different way to basically take these foreign polariton cavities and push them down, confine them down much further. And in that case, you are confined to an extreme degree, but you still have very high quality factors. In fact, the quality factor you have is limited by radiation, not by absorption. So this, as Vinod was saying, is not something I can prove, but like the material degree of absorption, the quality factor of absorption intrinsic to the material is in the order of 600 to 1,000. So it's much larger than the quality factors I'm actually measuring, which is a good indication that what we're measuring is really not limited by absorption, rather by something else. So we can think of this a lot more like cavities in the sense we're used to. Now, it feels a bit like half of this discussion is kind of an iteration of things that were shown by previous speakers. So I think like Dimitri gave 2 minutes recap of what hyperbolic polaritons are. I'll try to make an even shorter one just to kind of remind you what he was talking about. And the idea is really that we're comparing, that we're switching from normal optics where there is a diffraction limit and you cannot be confined to something smaller than the wavelength, because if your k in one axis is very large, then in the other axis it has to be imaginary. Okay? You're switching from there to this limitation, to this limit where this is just Helmholtz equation for anisotropic media, and if epsilon zz and epsilon xx have opposite signs, then you have just an hyperbolic relation, and basically the larger k is in one axis, the larger k is in the other axis. So there's no diffraction limit. You can have infinitely large wave numbers. I mean, infinite to the limit where if you're starting to approach the interatomic layer, interlayer distances in your wavelength, okay, then you will have problems. But in practical sense, it's unlimited. But you have the really weird caveat from the optics perspective that your light can only propagate on certain directions, certain angles, okay? And this gives rise to all of the rays Dimitri was mentioning. And now this is what I mentioned was for a bulk hyperbolic material. And it's worth mentioning what happens for finite slab, so just a flake of hyperbolic material, because then you get this type of dispersion. So you basically have here k equal to some material parameters through which the frequency dependency is arriving, plus two terms. One of them is just 2 pi n, some integer, and another one is also a combination of material parameters and the substrate parameters. So substrate or superstrate that you have. And there's some really weird properties to this relation already, because now you'll see that, first of all, the modes are no longer harmonic, okay? So it's not multiples of some base momentum, and they depend they depend directly on the thickness of the flake. So I make the flake twice as thin, I decrease the wavelength by a factor of 2, which is just odd. And there's a lot of other features to this. I'm go back to this point that the momentum that you have really depends on the substrate in a second, but this is basically what these modes can look like. So this is the mode for I think 25 nanometer thick HBN slab. So this is what the first mode looks like. This is what the second mode looks like. And if you replace your substrate with a metallic substrate instead of air, you're shifting the momentum, and you're also changing the shape of the mode, because it has to have a node here at the metallic layer. Now, these results, again, I have to give a lot of credit to Basov and Caldwell, who made a lot of these discoveries experimentally. And one of the first things people did after they had these materials at hand is start making cavities out of them. And this is a collection of cavity papers. This is basically the ones that are over here in the hyperbolic phonon polariton part. And you can see, if you look at the numbers carefully, that they're actually all hundreds of nanometers in size, and they're not much smaller. So you have to ask the question of why not smaller? And the answer should have been published in this paper, Nature Disasters, where people do experiments, fail, and then tell everybody, don't do this, okay? So I really wish there would have been the journal like this. It would have saved me a lot of time, because it turns out that when you're making these cavities smaller and smaller, you're literally cutting the HBN and you're damaging it in the process. And it seems to be an inevitable part of making HBN cavities. So you're always introducing some degree of damage, and that reduces the quality factors dramatically. So you can make a 20 nanometer cavity from HBN, but you'll go back to this quality factor of 5, and you didn't do much. So the idea we had was to abuse this fact that the substrate changes the momentum of the polariton, because if you have a substrate, which is changing abruptly, then you'll have some reflection at this interface, which means you can start, basically from impedance mismatch, you can start confining modes in areas which are limited from all sides by different substrates. So basically you have a hole in a metal, and in the middle, because of impedance mismatch, you have light circulating around. So that was the basic idea. And, doing it in the lab is a tiny bit more complicated, but, there's a lot of technical details you have to look into, but in the end, it is all about drilling holes in a gold. You have to drill really good holes, and it's a lot harder than it sounds, but you drill good holes, you put HBN on top of them, and that's it. Now, all we have left to do is to take it to the near field microscope, and Dimitri already told us about that. I hope you remember his explanation, because I don't have time to repeat it. It's basically going to be a measure, and what we're looking at is the signal is basically a measure of the local optical density of states. And if you're outside the Rostron band where you don't have these phonon polaritons, it's boring. When you go into the when you start going to frequencies where you have the phonon polaritons, you'll start seeing phonon polaritons appear. And this is the cavity, this is the resonance appearing, and it's popping up, disappearing, and eventually you also see higher order modes appearing inside of this cavity. And the notable thing here is how fast this happens in terms of frequency, because this is the picture at 13, it's just 2 inverse centimeter apart. Your profile of the response is changing quite dramatically. And you can just, to quantify this better, you can sit here in the middle, measure as a function of frequency, And you get plots like this with extremely narrow line widths, indicating very high quality factors. So here we're really, you can actually start to approach the limit where you're, the case where you're limited by your absorption. And it's really, yeah, just a very strong response, better than previous results, which is really fantastic. And you can take this further, okay, and to even smaller cavities. So this is a collection of slightly different techniques and slightly different types of cavities. In case you were wondering, PhD is, of course, pseudo-heterodyne. I don't know what you were thinking about. But you basically, you measure it in different ways, and however you measure it, you end up with something on the order of quality factors of 50 to 100 and something. And, you know, the exact number here is not so important because the number you have is very clearly from theory, from the best we can understand, is limited by leakage, because you're basically limiting, you know, impedance mismatch is the barrier that's preventing things from leaking out, and the limit of absorption is actually way out there. So we're not really even close to that. But then things become a bit funky, because you start looking at this analysis, trying to figure out what is your limitation? Is it impedance mismatch or absorption or what? And you'll find out that actually things are too good to be true. In what sense? I told you before we have a strong impedance mismatch between these two interfaces, but impedance mismatch, if you know your optics, is a really bad way to confine light. About 20% of the light is supposed to leak out whenever it reaches any one of these interfaces. So if you're really protected only by impedance mismatch, you would find in a very optimistic scenario, this is the theoretical maximum, which is about half of the experimental measurement. And I don't know about you, usually my experiments do not outperform my theory, especially not the idealistic, optimistic theory we had here. So that was a really odd case to consider. And then it got even stranger because we started suspecting something is going on. So we replaced the hole in the gold with the gold island. And in this case, you know, it's technically a bit complicated how to generate this and really keep things suspended, but you can do this. And now you have the same impedance mismatch, but both the near field measurement and the simulation shows literally no response. Okay, and that's really, really bizarre. And just to complement the picture, you can look at the actual cavity in simulation, and you'll see not only a strong response, okay, so it's, you'll see a lot of kind of indications that your interaction has higher order modes. So you see these undulations and ray-like behaviors, and there's a lot of really interesting physics here, which I will not have time to go into now. It's in the literature, but it's really about how these modes are actually interfering destructively on their way out, to which limits the total degree of radiation that you have outside of this cavity. So it's conceptually similar to what you see in bounding continuum modes, but a bit different because you have more modes and a lot of really interesting things here. On the context of this conference, I'll just say that, yeah, that you can basically reach cavities as small as 23 by 23 by 3 nanometers before your ability to measure them runs out. So this is the limitation. It's this small antenna limit that that Jerome was talking about. It's becoming really, really hard to get any signal, and this is a really extreme situation. And we're now actually working on also, and it's successful to integrate these cavities with graphene or other 2D materials. So that looks promising. I'll take you to a very, very, very quick tour to what happens when you have more than one cavity, because I think that's also something interesting to consider, because you know, if we're talking about designing the polaritonic vacuum, you can design it in more than one way. having arrays, it would also be very useful, especially if you can create, for example, Bragg cavities, which would confine also in terms of radiative loss. So, and the idea, but it turns out it's a lot more complicated than that, because if you have an array, a 1D lattice, okay, where you have some reflectors, okay, and it's, then for the first mode, you will have some band structure, say what you have here, but for the next mode, because it has different momentum, the band structure will be different, so basically shifted in energy. And if you now account for the fact that it's a hyperbolic material and you have an infinite number of modes, you have a complete and almost utter mess. And when I say almost, I say it because there is actually a small gap here, which is appearing for all of the modes, which is a bit odd. So why does it show up there? You can actually understand it quite intuitively if you go back to the equation for the momentum of the mode that we started with, because if this is your k and you can decompose it to some k0 plus integer number and multiplying another number delta, then you can start thinking about it in this way. If k0, the ratio of k0 and delta is a rational number, it means that if you start stretching out your supercell and you go further enough, there is a large enough unit cell at which the system, all of these modes are actually, you know, accumulating a 2 pi phase per round trip, or integer multiple of 2 pi phase, and therefore they all have a band gap. Of course, if this number is irrational, you do not, which is why you're getting a fractal structure reminiscent of Hofstadter butterfly in condensed matter physics, but it's actually a lot worse, because this is what you see here is the density of states for the simplistic case where the modes do not couple to one another, and in practice they actually can couple quite strongly from the zero mode to the first mode and so forth, and you're starting to get structures which are even more complicated. And what I really like about this is that these structures are basically extremely complicated band structures that you're getting out of a 1D system with literally nothing in it. This is just a simple periodic 1D crystal, and you already have these things. And we can also probe it experimentally, and also recently published results about topological behavior in this type of polaritonic cavities. Instead of going into that, I just want to finish, like I have 3 more minutes, and I want to go into results which are connected to what the chair of this session was actually presenting the other day, which is what happens, what else polaritons can do for us. Because I think it really adds a very strong degree of freedom when you start considering the fact that you have 4 vectors, like we were told yesterday, instead of, sorry, the day before, it's 4 vectors instead of just driving in omega. So the cartoon picture is that you can start tilting everything, and you have like transitions which are canted in a complicated way. And we were also working in this direction, and you really start to see really complicated band structures appearing. This is for graphene, which is driven, and I think the nice part is that you can not only see these structures, they become asymmetric, which is something very, very unusual for a band structure to have. Most band structures you have do not differentiate from right to left, and it's opening a lot of directions in this regard. One of them is looking at the photocurrent, because the photocurrent becomes non-reciprocal. It depends, you just drive the system, and it intrinsically wants to go to the right. And so if you start driving so this is the photocurrent we're calculating as a function of the Fermi energy, and you can see that basically for holes you will have one sign of the photocurrent, for electrons you'll have the opposite sign. That part is not surprising, but what's really, really strange is that if you're kind of here in the middle near the charge neutrality point, you still have a photocurrent. Electrons still want to, your charges still want to go to the right, and actually quite a lot of them, and it doesn't go to zero. Again, I think we're really struggling to understand where these results are coming from, and if you find them interesting, please talk to Ilya, who helped with the analysis. So and tell him what's going on here. With that, I'd like to thank all of my co-authors, and all the experiments were done in Frank Skopin's group during my postdoc. Theory was done with a collection of friends from Schwetz's group, Jacopo Torres' group in UPC, Netanel from Technion, Ilya from the audience, and material support we received from both the Japanese and the Kansas groups for HBN growth. I also want to thank my new group in Bar Ilan, which are all here. And just to really conclude by saying that, okay, I think like there's a lot of subtleties here that we have to be aware, because if we're too theory driven, we tend to forget what the material platform actually is, and also what the technical platform like the cavity actually is. So, and it can be really important, but that at the same note, I'm also very optimistic, because if you start looking at these tiny cavities and you're plugging in realistic parameters, the field magnitudes you're getting, or the band structure degree of modification you're expecting, is really quite large. So we're talking about megavolts per meter, tens of millielectron volts. I didn't know about this thing that you're supposed to exaggerate as a professor. So these are actually realistic numbers, and I'm hoping we can see them all soon.
Okay, so thank you very much. Questions? So maybe can I start?
Yeah.
So in your simulation of this quality factor, did you take into account your tip? Like there was a gigantic tip above your structure, wasn't it? Like a metallic chip. So
yeah,
doesn't that contribute something?
Yes. So that contributes quite a lot. So the results I showed were experiments. And
compare with the theory.
And to compare with the theory, yes, it does take out some of the some of the energy out. But I mean, it's the type of thing that you don't really want to account, because it feels like you're starting to put in a bunch of fudge parameters. Like I can, like, no, my quality factor is actually better because so it contributes, and it's really detail dependent.
Yeah. Is the tendency that it will help?
No. It's actually taking light out of the cavity.
Thank you very much.
So thanks for the interesting talk. I guess I maybe have two kind of questions. The first is actually, so in this so you started off the talk by sort of at least mentioning some of the efforts to do like modify ground states of systems with cavities. But so in this, given that this is the hyperbolic band in HBN, and you're talking about the thousands of wave numbers, I guess, what temperature would you need to go to thermally occupy this mode?
To thermally occupy it?
Yeah.
Yeah, the energy is 180-ish millielectron volt. Uh-huh. So yeah, that'll be very, very, very hot room. Yeah, thousands of degrees. Okay. So you don't want to thermally occupy. That's actually an advantage, that you don't have to think about that that much. Okay,
and then also, so what are the prospects for the intrinsic nonlinearity in the cavities? And if I want to, for instance, do for spectroscopic purposes, like coherent manipulation of the field beyond linear degree of freedom.
So this talk is recorded. Let's talk later.
Okay, thanks.
These band structures that you showed, where there were, like you said, there are some currents actually from one direction to another. So it seems like you're breaking the rotational symmetry, and right, so there. And I was just wondering, like those currents probably they're not protected with respect to some perturbations, right?
Yeah. Mm-hmm. No, I mean, you're breaking the symmetry explicitly because in the context of Takashi's talk, you're launching in polaritons. They're propagating in a certain direction. Mm-hmm. So you're breaking this. It's not a surprise that you're breaking, that the band structure breaks the symmetry.
So what is really the mystery there? What is really not understood?
I mean, I guess it would be just the fact that you have like directional photocurrent at charge neutrality. Usually, you know, if you have photocurrent, it at the very least flip sign at charge neutrality. Okay, because you're switching from electrons to holes.
Thanks.
Sorry. Yeah. One thing which, you know, you have these amazing cavities with extremely strong compression factor, which is really impressive. And you have them, of course, they appear within this Restreunten band, which is sort of limited. So now, when I'm looking at the physics of such a mode coupled to an electronic excitation, you know, if I just think of a strong coupling experiment, that I would have two polaritons, and they would be probably outside, then the eigenenergies will then be outside of that Restreunten band. So how should I think about this?
So I think you have two ways of thinking about it. You can think about it like you mentioned as in the non-resonant limit, okay, where your energy scale is very different from, so basically, you know, you're basically, it's a kind of the high frequency limit of the driving. But I think it's actually also quite interesting to look at it the other way around. What can we put inside of the cavity that will have this intrinsic energy scale of 180 millielectron volts? So there is actually crosstalk between these degrees of freedom.
Thank you.
A very beautiful experiment. So I wonder, how did you actually calculate the fluctuating electric field amplitude in your cavity? Because usually accounting for the total energy of these cavities is very difficult. You have different parts, you have negative refractive index, dielectric functions. So how is it actually calculated? Was that only by the cavity volume of that vacuum area?
No. Yeah, so this is referring to
yes.
This figure. Yeah, the hand waving version, okay, is just this formula you show at the start, which is just the square root. That's really not how you calculate it. You have to account for the electrostatic energy and the group velocity and a lot of these. It's like, yeah, basically I had a student do it.
Oh, so everything is accounted. Do you have a rough idea of how much energy was in the vacuum area where we can harness versus the energy distributed in the, say, hyperbolic material and also the gold, which takes some part of the energy as well?
So in this calculation, we were actually treating the gold like it was an ideal metal.
I see.
But,
okay.
but as a rule of the thumb, I would say it's half-half.
Okay, got it. Yeah, thank you. That's not bad, actually.
No,
it's very good. Thank you.
Any other questions?
Yeah, one last quick one. Very nice work on that. So I'm a little confused, also goes back to Jerome's question. I understand the use of hypercrystals if we want to get the light out, like what we did with quantum dots and so on. But if the goal is to change ground state, then the hypercrystals actually work against you, right? Because you're getting too much crosstalk between the cavities and you're actually folding the bands back.
Yeah.
So isn't it better to just stick with isolated cavities? I'm just asking, it's just a question.
No. The idea we had in mind was that we have so much radiative loss. If we can generate the band gap outside, then you will confine things inside. But I mean, if you just want to change I'm not sure that hypercrystals are the way to go to change the ground state. That's not what I was saying.
Okay.
Okay, if there are no further questions, let's thank the speaker again. Thank you very much. And we will have a coffee break.